Hi, I'm Mr. V, and today we're starting Unit 6 of the Illustrative Math Geometry course. This is coordinate geometry, and this is the rigid transformations in the plane. By the end of the course, end of the day, you should be able to say, I can prove triangles are congruent using coordinates, and I can reflect, rotate, and translate figures in the coordinate plane. So the first question was, how far is it from point A to point B? What transformation will take point A to point B? I will copy this over and work through this. You should try this on your own before listening to my response, but for your benefit, I'm doing this here. And so, if I can find my pen. To go from point A to point B, some people said it's 7 because you're going to go 4 across this way, which is true. You start at 0, 1, 2, 3, 4, 4 across. Some people started in saying 1, 2, 3, 4, but that's not correct. When you're sitting on this point, that's at 0. It isn't until you move that you go 1, 2, 3, 4. So this would be 3. And this is a total of 4, but if I go the way the crow flies, it'd be this distance. We recognize that this is a right triangle because it follows along the grid lines. The grid lines are for horizontal and vertical are 90 degrees. So I can use the Pythagorean theorem. A squared plus b squared is equal to c squared. And I'll substitute the values. 3 squared plus 4 squared, that's 9 plus 16 is equal to c squared. When you square root to both sides, you have the square root of 25. When you square root something, you're going to have a plus or minus. We're going to ignore the negative root because this is geometry and we're looking at a length. So our c value, our hypotenuse, is 5. The length here, the distance is 5. And there's several ways that you could talk about this. There are 3 rigid motion transformations. One is to translate. One is to rotate. And one is to reflect. Now, if you're translating, you have to specify the directed line segment. So you could specify, I'm going to translate from A to B by directed line segment from A to B. You could have said, I'm going to translate from -3, 4 to 1, 2. And another way of writing this is, if I start at an xy coordinate, I'm going to translate using an arrow here to the x value plus 4 and the y value minus 3. That's another way of writing this. If you're going to rotate, you have to specify what you're going to rotate around. And we're going to rotate around the midpoint of segment AB. So midpoint of segment AB. You have to specify what you're rotating around, how many degrees it is. It would be 180 degrees. If it's 180 degrees, you don't have to specify clockwise or counterclockwise because they're the same. But otherwise, you would have to tell what point you're rotating around, how many degrees, and whether it's and the direction, like clockwise or counterclockwise. If you're reflecting, we have to reflect across a line. So you have to specify the line. I'm going to specify that it's the perpendicular bisector of segment AB. Bisects is going to pass through the midpoint. It's got to be perpendicular. This has a slope of 3 over 4. To be perpendicular, it'll have to have a slope of 4. 1, 2, 3, 4. 1, 2, 3. So it'll go like this. When you reflect across, it's going to be perpendicular to this line, and it's going to cut this into 2 equal parts. So there's going to be equal distance on either side of the line. And you must specify those things in order to tell me what a transformation is. Our next activity was transforming with coordinates. And so we had a GeoGebra activity. And you were to try to do it with the GeoGebra. You could also do it by hand. And if you wanted to watch this video, this would show you how to do it. I'll show you here what I did in the video. And we're going to rotate figure H 90 degrees clockwise using the center at 2, 0. Translate it from 2, 0 to 3, -4, and then change the color. We're also going to take that original figure, H, and reflect it across the y-axis, and then rotate it counterclockwise 90 degrees. So here's my figure. I will start by rotating it. I'm going to rotate it around this point, so I have to specify the point at 2, 0. We're going to rotate it using the rotation tool clockwise 90 degrees. 90 degrees, so I'll mark it clockwise. And then I'm going to take this figure and translate it by a directed line segment, or a vector, from 2, 0 to 3, -4. So it's going to go this far. The whole figure is going to go that far. So I'll use my translate by vector. I'm going to translate this figure, not a point. I'm going to translate the figure, the entire figure, by this much. I'll make it smaller so that you can see it, and move it so we can see it. And I'm supposed to change this to green. To do that, I'll use this hamburger with the Geogebra insignia on it. And I'm going to change the label to, I think I'll change it to R. The name will be R. I think that's what we're supposed to do. Name it R. The next one will change it to L. So here we're going to reflect this across the y-axis. To do that, I need to choose my tool. I'll use the transformation tools. Reflection is this one. Reflect this across the y-axis, and we'll rotate it about the origin. I need to point the point for the origin here, and we'll rotate it using the rotation tool. Rotate this figure about this point, 90 degrees counterclockwise. And there we have it. We can also change the color of this. I'll make it orange. And I'll do this with this color. And I'll also change the name of it using the gear tool. The gear tool changes the name to L. And I'll also change this color just for grin so that you can see that I've translated. Here we've translated, we've rotated this 90 degrees and translated it. Here we've reflected it and then rotated it around a point. This point was one of the vertices, this one was not. And you can see that. You could have done this by hand. This is to try to get you to see what's going on. We'll be looking at the actual coordinates and how we would do this with a formula down the road. In this activity, we're going to calculate the side lengths and the angle measures of the triangles in a coordinate plane. We'll demonstrate that the two are congruent, and finally we will specify a sequence of rigid transformation that takes one onto the other. We can leave our answers as exact, or we can round to the nearest tenth for sides, nearest degree for angles. And here is our figure. Let me copy this over, and I'll use this for my demonstration for this lecture. You should try this on your own. Here we're finding the side lengths. Here we're finding the angles. We're going to talk about why they are congruent, and then we're going to show a transformation, talk about a transformation that would achieve this. So if I go to the next page, I can look at the drawing and count on the grid. Here I have 1, 2, 3. This distance is 3. How did I find it? I counted along the grid. This is 2. I found it by counting along the grid. Again, 2 and 3. To find the hypotenuse of either one of these, I'm going to use the Pythagorean theorem because this is a right triangle. This is a right angle. Because of the grid lines, I can see that. So I use a squared plus b squared is c squared. And we'll substitute the values. 2 squared plus 3 squared is equal to c squared. 2 squared is 4, 3 squared is 9. So 13 is equal to c squared. And when you take the square root of both sides, again, anytime you take the square root of one side of an equation, you have to take it of the other side. And anytime you take a square root, you can have a plus or minus. We're going to ignore the negative root because this is a length, so it's going to be a positive. And if you wanted to, you could approximate this at 3.6. So this is about 3.6. Same with this one. And now we need to find the angles. We've already found the one. To find this angle, angle A, we're going to use the opposite divided by the adjacent. That's going to be the tangent. So the tangent of angle A is equal to 2 over 3. We need to find the angle, so we'll use the inverse tangent. The tangent of an angle is equal to a ratio. The inverse tangent of a ratio is equal to the angle. So that's equal to the measure of angle A, which I think is 34. Let's just check, see what some of the other students said. Some of my students said it was 33.6. So we'll round it to the nearest degree, 34 degrees. And then to find the other angle, we'll just subtract that from 90, because 90 plus 90 is equal to 180. And so this has to equal to 90. So if this is 34 degrees, my other angle would have to be 56. 56 degrees. And the same thing is true over here. So this would be 56 degrees, and angle D would be 34 degrees. Now, the question was, how do you know that they're congruent? Well, all 6 of the measurable parts, all 3 angles and all 3 sides of one triangle are congruent to all 3 measures of one to the other. We know that 2 objects are congruent if you can map the pre-image onto the image with a finite set of rigid transformations. And here we haven't described the transformations, but all of the parts are congruent. Sometimes we would say the corresponding parts of congruent triangles are congruent. And I'm going to say it out every time, even though I may abbreviate it CPCTC. If I didn't say it, you might think this stands for cotton, popcorn, candy, treats, candy, something like that. I don't know. Anyway, to translate to transform this, one way to possibly do it would be to translate by directed line segment from D to A, or if we're going the other direction, from A to D, in which case this would end up here. And then you could rotate it 90 degrees. And rotating it 90 degrees will end up on top of this one. Now, what single transformation would take triangle ABC to DEF? And I give you a GeoGebra app that you could actually do this with. So we're going to take this one onto this one with a rotate. It looks like it's going to be a rotation, because here's a 90-degree angle, here's a 90-degree angle. And I'm not exactly sure where that point is. I'm going to show you in a moment where it is. So if I'll estimate it's going to be here, and I don't think that's right, but it might be right. So we'll do the rotation using the rotation tool. Rotate this object around this point 90 degrees, because the line's going straight up and straight down, or straight up and straight down. So, and this will be counterclockwise. So I do it here, and it's not quite where it's supposed to be. But if I move this point, and I move it down, no, if I move it here, so I would rotate around this point. And one way to know how to do this is to use the perpendicular bisector. And if you've done constructions and had me with term 1, you would understand, oh, the perpendicular bisector is where this point of rotation is going to be. And you can know this because every place that you have there is going to be equal distant from that point of rotation. We're going to actually rotate it around a circle. So here, this circle, here, this circle goes to B prime, and here this circle goes to C prime. Now, in this activity, you showed that all 6 parts of one triangle were congruent to the 6 parts of the other, 3 sides and 3 angles. This was a review of what was done in first term in geometry. And we used CPCTC, corresponding parts of congruent triangles or congruent figures are congruent. But wait, was it necessary to show all parts of every pair of corresponding parts was congruent in order to show that the 2 triangles were congruent? What theorems or shortcuts do you remember or know that you've used to do this? And for some of you, it's been a long time, so I'm going to just show you what these shortcuts are. There are valid shortcuts, and there are some shortcuts that are not valid. So for the valid shortcuts, we have the side, 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 triangle congruence theorem. We have the angle, side, angle, side, angle, side, angle, angle, side, because if you know two angles, you know that the third angle is good. So angle, this is just angle, 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 side, angle, and with an extra angle in it. We also have the hypotenuse leg. And that's special for right triangles. And then it goes us to invalid shortcuts. I'll do that here. The one is called SSA, which is something nasty backward. We call it the donkey theorem. It's invalid. You can't use it. And AAA, which is just auto insurance. Why don't these two work? Let me draw you a little diagram to show it and demonstrate it. The auto insurance, the donkey theorem doesn't work. Here's an example. If I have an isosceles triangle like this, I have two sides that are congruent, and the isosceles triangle theorem tells me that the base angles are congruent. So I have an angle and a side, angle and a side. And if I draw this third side like this, now I've got an angle, side, side, angle, side, side. These two triangles don't even look congruent. They're not congruent. This is why the donkey theorem doesn't work. If I had angle, 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 here I have a right angle and two other angles. And I could also draw this same triangle like this with the right angle and these two other angles. You can see it's a dilation. It does not mean that they are going to be congruent. So with that in mind, go on to the synthesis of this lesson. In the synthesis, you can make a drawing like this. You can put it somewhere else on the figure. So if I go like right here, 1, 2, I'm going to go 1, 2, 3, 4, 5, 6, 1, 2, 3. 1, 2, 3, 4, 5, 6, 1, 2, 3. I'll go to this point, I'll go to this point. And then we need to show that these two triangles are congruent. We mark them on the map, and we can prove this. And we can prove this using side, side, side. I know that this side is a length of 3. Oops, let me mark with my pen. This side is a length of 3. This side is a length of 3. I can determine the length of both of these sides by making it into a right triangle. I'll do this one here. I can show you, I can make this into a right triangle. And then using my length and my width, I can find this length. I could also make this one into a right triangle. And using my length and my width, I can find it. Doing the same thing with this other triangle. If I show that all three sides of the one triangle are congruent to all three sides of the other triangle, then I've accomplished my task. And that was how I would do it. There are other ways, I'm sure. I could say I'm going to translate this from this point to here, rotate it 90 degrees. That would be another way of doing it. And then there's the cool down. And the cool down, this triangle, A prime, B prime, C prime, is congruent to triangle A, B, C. And your task is to translate, to transform these so that you can show that they are congruent. One way of doing this would be to, there's several ways of doing it. One way would be to take the triangle ABC and to reflect it. What are we going to reflect it across? You have to have a line you're going to reflect it across. So we're going to reflect it across the vertical line at A. When I do, this is going to end up at A. This will be 1, 2, 3, 1, 2, 3 on the other side of this. Here we have 1, and this would be 1. So this would be my new triangle. And now I can just translate this from A to A prime. Every point will translate the same amount from here to here, from here to here. And that would get me there. You could also do a translation, a rotation, and a reflection. There are other ways of doing this, like I said. And that's what we discussed today. So it's really about refreshing your memory on triangles being congruent, what it means to be congruent, what it means to say that their sides and the angles, the shortcuts that we have that can show that they're congruent, and to talk about transformations. And we'll talk more in depth tomorrow. Good luck and success.